In this lecture, we're going to start a topic called stress and strain transformations. It'll be over the next few lectures that we'll talk about this, but today we're going to start off with talking about transformations of plane strain. Before we get to that, though, let's just kind of introduce this topic. Stress and strain transformations kind of sounds a little bit unusual at first, and we've already done it, though. So here we have on the left a bar that has an axial force. And we know that if we were to sketch the stress state in that bar, that stress state on that little stress block or stress element would be what's called a uniaxial stress state. And we would say that the stress sigma is equal to the force divided by the cross-sectional area, or P over A. And then a little bit later on, at the beginning of the course, we talked about how we could find the maximum shearing stress in the bar. And the maximum shearing stress was at 45 degrees. To the axis of the bar. This sigma is equal to P over A. This is actually the maximum normal stress. And those maximums are kind of important. If a material is going to fail, they will typically fail due to either the maximum shearing stress or the maximum tensile stress. There are some exceptions, of course, for different materials, but we can kind of generally classify what are known as brittle materials as those that are more sensitive to normal stresses, and ductile materials as those that are more sensitive to shearing stresses. So we went through and we talked about axial loading and so forth, and then we got into a section on torsion. And then we said, okay, let's take a look at a bar in torsion and calculate the stress state from a torque. Well, if this is my torque T, my shearing stress state will be on the outside of the bar given by the formula tau is equal to the torque times the diameter over 2 divided by the polar moment of inertia. And we have a shearing stress state in this orientation. And the maximum normal stress is at 45 degrees. To the axis of the bar. And we went through and we saw how to transform that state of stress to get the stresses on the inclined plane. And so that's what stress and strain transformations are, trying to look at our stress element or our stress block and transforming that to an element oriented in a different way. Let me switch back to my blue color here. Another way to show that then is on this block. This would be my generic stress block or stress element. There could be some stresses that act in this material in these directions. They could be shearing stresses and normal stresses in different directions. What we're trying to do, it's kind of hard to show this. Maybe I can make a copy of this piece right here. But if you could imagine our starting stress state in the X and Y system as I have drawn here, what I can do is I can take this block and I can rotate it to different orientations, different angles from the original X and Y axis. And I can have stress components that are in what are known as the X prime and Y prime directions. These components will change as this angle changes. And so the goal of these lectures is to find out these new stress components in that new orientation, which we're going to call sigma X prime, sigma Y prime, and tau X prime Y prime that are expressed in terms of the original coordinate stresses sigma X, sigma Y, and tau XY, and the angle of rotation, which could be positive or negative, which we're going to call theta. So what we're going to do is we'll learn how to do this. We're going to derive the equations for these plane stress transformations, then do something similar for strain. And then we're also going to use something called Moore's circle of stress. Now, Moore's circle of stress is a graphical representation of the stress transformations that we're going to get. It's very useful for visualizing the size and magnitude of stress states and picking off these critical maximum normal and maximum shearing stresses that we can use for later on in failure analysis, determining whether something will fail or not. We'll get to that at the very end of the course. Well, we're going to do this not for just any particular stress state, but we're going to do this for what's known as a plane stress state. Before we get into the ideas and the concepts of plane stress, let's just review what a general state of stress will look like. So we'll start off talking about the most general state of stress in Newtonian mechanics, the three-dimensional stress state. We've talked about normal stresses and shearing stresses, and since we live in a three-dimensional world, we can pull out a cube of material from any structure that we want, and we can find a normal stress and two shearing stresses on each of the faces of the cube. So here I have a cube sitting in the x, y, z coordinate system, and I can label these stresses that act on here a normal stress sigma x that points in the x direction and is acting on what is known as the x face, a stress that points in the y direction, sigma y, and a stress that points in the z direction, sigma z. So all of these three are normal stresses. That arrow looks a little funny there. Let me see if I can get that looking just a little bit nicer. Maybe pointing off in that direction. So those are the three normal stresses. It's pretty easy to pick out the normal stresses. They point in the direction of the coordinate axis. The shearing stresses, the way they're labeled, here's one that I'm going to draw in. It goes this way. You notice it is on the x face and it points in the y direction. So we're going to label that tau xy. And we know from previously when we talked about shearing stresses that shearing stresses at right angles are equal. So this shearing stress that is in the y face pointing in the x direction could be called tau yx, but those are equal. There are two more pairs of shearing stresses that we can have. This pair will be known as tau yz. Let me draw a little line to them. And then this pair here will be known as tau xz. Okay. So those three normal stresses and three shearing stresses are known as our full state of three-dimensional stress. Now it is possible to transform this stress state. You can imagine taking this cube of material and rotating it in space. And the components sigma x, sigma y, and sigma z, tau xy, tau yz, and tau xz will all change as you reorient this cube. You can think of it like a die, like a dice from a set of dice, a single die. You can move that around in space, and those values of those stress arrows will change in a certain way. Just as a little bit of information that you may be interested in, the full three-dimensional stress transformation is beyond the scope of this course, but if you take advanced courses in mechanics materials or something called theory of elasticity or continuum mechanics, you will deal with the full three-dimensional stress transformation. And it turns out that stress is something called a tensor, in which case we can write our stress components in such a way that we have sigma x, sigma y, and sigma z, the normal stresses along the diagonal, and the shearing stresses on the off-diagonal terms, tau xy, tau xz, tau yz, and then a symmetric tensor here, a symmetric matrix of components that is called a tensor. You may have not heard the word tensor before, but you've surely heard the word vector. If you can recall, a vector can be expressed as a column of numbers, while a tensor can be expressed as a matrix of numbers. And we can do certain matrix operations on this set of components to do these stress transformations. If you take a class in linear algebra, then you may have some experience with diagonalizing the matrix, with doing some other operations on matrices. Turns out that although a tensor can be expressed as a matrix of components, not all matrices are tensors. But certain tensors can be expressed as matrices. Well, that's a little bit beyond the scope of this course. So what we're going to do is we're going to back it off a little bit and talk about something called plane stress, and then later on generalized plane stress. So let's write this down. So here we have the full three-dimensional stress state where I have all the stress components. In plane stress, what we have is a situation where all the non-zero stress components lie in one plane. Let's write that down. Now, most books tend to choose this plane to be the X and the Y plane. It's not necessary that it always be the X and the Y plane. It can be the X and the Z or the Y and the Z, whichever plane has the set of non-zero stress components. But the idea is, if we were to take this cube and get rid of some of the stresses, but keep only stresses in one plane, I'll do like most books do and leave the XY plane, we would have sigma X, sigma Y, and tau XY that are left. Sigma Z, tau XZ, and tau YZ being equal to 0. Then we have what's known as a state of plane stress. Now, I've drawn, because of the perspective on this cube, I've drawn some stresses, but there are also stresses that are pointing in the opposite directions on the hidden faces of this cube that you can't see. So another way that we'll sometimes draw this stress state, it's like I drew on the first slide, is if I look down the z-axis, I look at this face right here down the z-axis, I have my X and my Y coordinate system, and then I have my stress components that are non-zero, sigma X, sigma Y, and tau XY. So this is just another way to show this cube is to draw it flat, but still we need to keep in mind that the object is three-dimensional and the stress state can have a third component to it in the z direction that we may have to account for. All right, so now we know what plane stress is. We're going to talk about transformations of plane stress. There are certain situations where we need to find stress components at some angle in a material, or another way to say that is for a rotated set of axes. So here I have a material that's got a stress state that I have on my little block that I'm indicating here, sigma X, sigma Y, and tau XY. And maybe there's a reason why we might want to find these stresses off at a new angle. Suppose we have a plate of material where we have this stress state, and off at some angle in this material is some weld line. Now, one thing you may know about welds is that welding can change the material properties locally. There can be some weakened material in what's known as the heat affected zone, and we may be interested in finding the stresses that are off, pulling this weld apart. But it's easy to calculate the stresses in the original XY coordinate system. So what we would need to do then would be to transform our original X and Y coordinate system stresses into this new coordinate system where we can find the normal stresses and the shearing stresses off at that particular angle. So if this was the horizontal axis, there's perpendicular to the weld line. This would be what I call my x-axis and my x-prime axis. Here's my y-axis, and then my y-prime axis would be off this way. And that would be the same angle theta if we keep those coordinate systems at 90 degrees apart. So we may be interested in finding my stress components, which I can call, in this case, sigma x prime, which should be on this side as well, tau x prime y prime. And we might be interested in the stresses that go perpendicular to that as well. I'll put them in red. The set of shearing stresses and the normal stress that goes along the weld line, which I will call sigma y prime. So if we can think of a little square of material in here, we have that picture like I showed on the first page, where we take this block and we rotate it to a new set of coordinate axes. Okay, so we're rotating this. We can go rotate it this way, we can rotate it that way, and as we rotate it and align it with our new axis, which we call the primed axis, I'll put little primes on these. These components will change as a function of the angle theta in our original starting components. Now there's another way to show this, and a lot of books show this to begin with, and it's easy to derive these equations this way, and that is with a wedge instead of taking a look at a square that rotates. We're going to want to use both concepts in this class. So if we can imagine cutting this wedge at an angle like this, and drawing that triangle. It's actually a wedge in 3D, but as we look down the z-axis, it's a triangle. Drawing this, of course, we have our starting components of stress, sigma x, sigma y, and tau xy. We may be interested in finding the stresses on this inclined plane, which we're going to label sigma n and tau in t. Now, the sigma n, we're also going to use the notation sigma x prime from time to time, and the tau in t is going to be the same as in that other picture where we use the notation tau x prime y prime. All right. So what we're going to do next is we're going to go through a little bit of geometry, a little bit of algebra, and equilibrium to determine what these formulas are for the stresses sigma n and tau n t on that inclined plane. We're going to derive some equations. We're going to get a chance to use those equations for some homework, but we need to show how they come about first. All right. Now, to apply equilibrium, there's no such thing as the summation of stresses equal to 0. We're going to have to apply the summation of forces equal to 0. So the first thing we need to do is we need to take our stress state from that wedge and convert those stresses into forces, and we can do that by multiplying them by the areas on which they act. So here's what I mean by that. Here in 3D is this wedge, and let's give this some dimension. Let's call it a symbol T for the thickness. In this long direction, the hypotenuse of that triangle, let's call that distance L. So the area of the inclined face, I'm going to call A, and it's going to be equal to L times T. So in order to convert this sigma n into a force in the n direction, I'm going to go to this, redraw this block again. The force in the n direction is going to be sigma n times the area A on which it acts. In the same way, I can get a shearing force that's going to be equal to tau nt times that area A. And with a little bit of algebra, a little bit of trig, I can find out the areas of those other two faces on the back and bottom sides of the wedge. So we need to define this angle theta, and most books define this angle theta in this way, so we're going to do it. It doesn't matter if you use this angle or you can use this angle down below. The procedure's the same. The equations will look a little different if you use the other angle. So we're going to stick with the convention that most books use and call that the angle theta. Now, this dimension, if we know the slant length L and the angle theta, that dimension is going to be L times the sine of theta. And this dimension is going to be L times the cosine of theta. So what that means is the area on the bottom, I'm shading in right here, which I will call a y, because it's perpendicular to the y-axis, is going to be equal to the thickness T times L sine theta. The area on the back side, it's going to be, we'll call that AX. That's going to be L cosine theta times the dimension T. And if you notice, T times L shows up on both of these, but we know T times L is the area of the inclined plane. So another way I can write this then is that the area of the bottom is equal to the area of the slanted plane times the sine of theta, and the area of the AX on the back side is going to be the area A times the cosine of theta. So we can get the forces that point off in these directions by doing, multiplying the stresses times those respective areas. So on the bottom, we have the force that's going to be equal to sigma y times the area A sine theta, a shearing force that'll be equal to tau xy A sine theta, a force off in this horizontal direction that's going to be sigma x A cosine theta, and then a shearing force over here that's going to be equal to tau xy A cosine theta. What we can do next then is we can apply the summation of forces. If we want to solve for sigma n and for tau nt, the easiest way to do this is if we do the summation of forces off in the n and the t direction. So let me write down those equations and then we'll go through them. Let's just go through them as I talk. So the summation of forces in the n direction, we'll take off to the upper right positive, would be sigma n times A. And then each of the other four forces that are not on the inclined plane will have a component of that force in the n direction. So for example, let's take a look at the force components that I sketched in with the red dashes. Sigma x A cosine theta is the force, and it has a component that goes in the minus n direction. So I'll have minus the force sigma x A cosine theta, and then the component, let's see, that would be the cosine theta component. Okay, so in the bracket is the force, and then this is a component of that force. Now, each of these other forces that act on this wedge can be broken up into components in the n and the t direction. And I'm going to let you complete that, but I'm going to write down the formula that we get. If I do the stress, the force on the bottom pointing vertically down, I have sigma y A sine theta times the sine theta component. I'll have the shearing stress, tau xy A cosine theta, okay, that's on the left side, times the sine theta component, and then tau xy A sine theta and the cosine theta component. And if the object is in equilibrium, those will be equal to 0. In the same way, then I can also have the summation of forces in the t direction. I'll have the force tau nt times A. Now this component is in the positive t direction. The force sigma x A cosine theta. We have the sine theta component minus sigma y a sine theta. That force times the cosine theta component. And then in the negative direction, tau xy a cosine theta. And with the cosine theta component, and then a plus tau xy a sine theta in the sine theta component equal to 0 for equilibrium. Now, of course, we can divide through each of these terms by a. They all have the area a in it. And if we know the value of the angle theta, we can use these equations directly to solve for sigma n and for tau nt, those stresses on the inclined plane. Let's do a little bit of algebra on these equations, and we'll write them in a more usual form. But if you just need those numbers and apply what's called the equilibrium approach to stress transformation equations, then our work is done. And so by dividing through by a, we get these equations on top in terms of the angle theta. And we can also apply some trig identities to rearrange these equations and write them slightly differently in terms of the double angle. So let me write down a couple trig identities here. We have 2 sine theta cosine theta is equal to the sine of 2 theta. We have cosine squared minus sine squared of theta is equal to cosine 2 theta. We have an identity that says sine squared theta is equal to 1 minus cosine 2 theta over 2. We have another identity that says cosine squared of theta is equal to 1 plus cosine 2 theta over 2. So we're going to do just a little bit more algebra and write these in terms of the double angle, and we'll find out why we want to do that later. For now, you can use either the single theta equation or the double theta equation. All right, and so there's those equations written in terms of the double angle 2 theta. So let's mark this up just to keep these straight. Both set of equations are equivalent. This one is in terms of theta, and these are in terms of 2 theta. I'll let you do the algebra to verify that I've done my algebra correctly. All right, so if we have then our wedge, where our stress components sigma x, sigma y, and tau xy are known, and the angle theta is known, then we can use these equations to find our stress, sigma n and tau nt. It's as simple as plugging those numbers in and getting values for those stress components. There's one little thing we have to take care of, though. Our other interpretation of stress transformation, we said, was to take our original square and rotate that square to a new coordinate axis, sigma x prime, sigma y prime, and tau x prime, y prime. So in this case, we start with our stresses that look like this in our original x and y axis, and we want to find the new stress components off at some angle theta from the original x-axis. And we call these stress components sigma x prime, sigma y prime, and tau x prime, y prime. So we need to do a little bit more work to figure out what sigma y prime is. That's called the stress on the orthogonal face. And what is meant by that is it's the stress that's perpendicular to the x prime direction, which we can show on this block, but we can't really show on this block where we have sigma n and tau nt. All right, so it would be the stress, I guess, sigma t, the normal stress that acts on a face that's perpendicular to the t direction. We call that sigma y prime. There's an easy way to figure out what this stress is, however. If we take a look, this stress component, sigma x prime, what that is simply sigma n, where we plug in the angle theta. Tau x prime y prime is the same as tau nt, where we plug in the angle theta. But because the y prime axis is 90 degrees apart from the x prime axis, the shortcut way to figure out what sigma y prime is to use the sigma n equation, but we plug in theta plus 90 degrees. Okay, so let's do that on the next page. All right, and so with a little bit of algebra, then we can put in theta plus 90 degrees, and we get, let me highlight it over here, sigma x cosine squared theta plus 90 degrees plus sigma y sine squared theta plus 90 degrees plus 2 tau xy sine theta plus 90 cosine theta plus 90 degrees. And we end up, in terms of theta, with this equation, sigma x sine squared theta plus sigma y cosine squared theta minus 2 tau xy sine theta cosine theta. And in terms of the double angle, we end up with shifting our trig functions by 180 degrees, which changes the sign of the cosine and the sine function. So we end up with sigma x plus sigma y over 2 minus sigma x minus sigma y over 2 cosine 2 theta minus tau xy sine 2 theta. Okay, so let me write down the complete set of equations here, and we'll take a look at them. I will say right now, however, in my class, I do not want you to memorize these equations. I want you to see where they come from. I want you to understand how they work, but I don't want you to memorize these equations. So let's write them down all on one page here on the next page. Okay, so here's these this full set of plane stress transformation equations for sigma x prime, sigma y prime, and tau x prime y prime. As we said before, sometimes we're going to use the x prime y prime notation. Sometimes we're going to use the sigma n and tau nt notation. So this can also be written as sigma n, and this tau x prime y prime can also be written as tau nt. Now, if you look at these equations kind of carefully, you may notice something. If we add together the sigma x prime and sigma y prime equations, what we're going to get is these first two terms have sigma x plus sigma y over 2. If we add them together, since there's two of them, we have sigma x plus sigma y. And these next two terms annihilate each other. They cancel out. They're the same terms with opposite signs. So this is kind of handy sometimes. Note that sigma x prime plus sigma y prime is equal to sigma x plus sigma y. This doesn't hold in the full three-dimensional case, but this does hold for what's known as a state of plane stress, or later on, we're going to talk about something called generalized plane stress. But this gives you a shortcut method to allow you to calculate sigma y prime. So you can rearrange this equation and say that sigma y prime is equal to sigma x plus sigma y minus the sigma x prime that you can calculate from the big long equation. That's kind of handy. The fancy way to say this is that the sum of those two normal stress components for plane stress is invariant to coordinate rotation. And again, that may be something that you encounter if you take a more advanced class in mechanics of materials, theory of elasticity, or even maybe linear algebra with some different terms that they may use. All right. So the last thing that we need to talk about is how to use these equations. Well, first of all, I would never personally ask anyone to memorize these equations. So I'm going to put this here, don't memorize these equations. It's too easy to mess these things up. Don't program them into your calculator either. It's just not worth it. Later on in the next couple lectures, we're going to learn about something called Moore's circle of stress, which is a graphical representation of these stress transformation equations. So don't memorize these. But we do need to know how to use them. Sometimes if you're programming a computer, setting something up on a spreadsheet, it may be easier to use these equations in this form rather than Moore's circle. But we don't have to know how to use these equations. So let's take, as an example, a state of stress that looks like this. We'll use some numbers here in a minute. But let's talk about how these equations are used. We have an X and a Y coordinate system. And these are the positive directions for these stress components. So a positive normal stress is in tension. And that makes a lot of sense. We've talked about the sign convention for normal stresses already. We haven't really talked much about the sign convention for shearing stresses. We kind of ignored it because we're mainly interested in the magnitude of shearing stresses up until this point. But once we put a coordinate system on our block like this, we can identify what's known as a positive shearing stress. A positive shearing stress will act on the positive X face and point in the positive Y direction, with these other shearing stresses keeping this thing in equilibrium. So all of these stress components that I have here are positive stress components. So if the stress components really point in these directions, in these equations up here, you will use positive numbers. We also need to define the angle of a positive rotation theta. The angle for a positive rotation theta is from the x-axis to the y-axis. That would be counterclockwise. So if we go off in this direction, then we use a positive angle theta. If we go in the opposite direction, if we go clockwise, then we would put in a negative value for theta. Into those equations. So for example, if theta was 20 degrees this way, if theta were 20 degrees, what I would put into the equations would be theta is equal to minus 20 degrees. And if theta in this case were 30 degrees, what I would put into the equation would be theta is equal to plus 30 degrees. So you need to know this sign convention. Again, let's say it again. Positive shearing stresses are on the positive X face and point in the positive Y direction. Positive normal stresses, sigma, are in tension. So be careful with that sign convention. All right, let's make a little bit of room and let's do an example with some numbers. All right, so for this example, let's find the values of the stresses sigma x prime, sigma y prime, and tau x prime, y prime on a rotated block that's rotated counterclockwise by 30 degrees. Our original stress state in the x and the y coordinate system is sigma x is 20 megapascals, sigma y is 10 megapascals, but notice that it's in compression, and then tau xy points in that direction that's shown there of 10 megapascals. So let's write down what all of our values are. In this case, since sigma x is in tension, it's going to be a plus 20 megapascals. Sigma y is going to be a negative 10 megapascals because it's in compression. Tau xy will start off and it will be a minus 10 megapascals because if you notice it's pointing in the negative y direction on the positive x face. And then our angle theta, since the angle theta is counterclockwise, the angle theta will be plus 30 degrees. So all we need to do is first find our sigma x prime. All right, so if we remember those equations, we got a sigma x plus sigma y over 2. And I need to put in a negative 10 right there. We have plus the quantity, sigma x minus sigma y over 2. We're using the double angle formula, so we're going to have cosine of 2 times 30 degrees, and then plus tau xy, which happens to also be a minus 10, sine of 2 times 30 degrees for the double angle formula. And for this value, I get 3.84 megapascals. For sigma y prime, I can use the full equation. I'll have 20 plus a negative 10 over 2 minus 20 minus a negative 10 over 2 cosine of 2 times 30 degrees minus a negative 10 sine 2 times 30 degrees. And from that, I will get 6.16 megapascals. For tau x prime y prime, I have minus sigma x plus sigma y over 2 made a mistake in my equation. Let me fix that. It's a good reason not to try to memorize those equations. Here we have minus sigma x, and this should be inside this quantity, negative of the quantity, sigma x minus sigma y over 2 sine 2 theta. And then we have plus tau xy, which is minus 10 times the cosine of 2 times 30 degrees. And when I put all those numbers together, I get negative 17.99 megapascals. All right. Now, we didn't have to use this long equation for sigma y prime. Let's take a look at this. If we have sigma x prime, we had that equation, sigma x prime plus sigma y prime is equal to sigma x plus sigma y. Sigma x plus sigma y, if we look at that, is plus 10. So sigma y prime should have been equal to 10 minus sigma x prime. And indeed, if we do that calculation, we will get 6.16 megapascals. All right, so this is just a simple example on how to use those equations to do stress transformations. Now, most books will have you do a couple homework problems where you use these equations to find stresses off at some angle. We need to know how to do that, but we're going to spend most of our time learning how to do this with another technique in the next lecture, talking about Moore's circle of stress.